Let's say you are given a graph like this. Now how to represent the same graph in another way? It's not about just redrawing. Like if you give me the information, you can draw this graph with that information. Like now we are going to collect information in terms of adjacent vertex. Here there are 6 vertices, right? So for each vertex we will try to understand what are the adjacent vertices. So here for A, what is the adjacent vertex? Adjacent vertices are F and D. And when it comes to B, so the adjacent vertices are E, F, yeah, and C. I'm writing C and E alike. Okay, let me make it different. Now for C, there is only one adjacent vertex, that is F. Now similarly the other, um, for D, they are E and A. Okay, A, E, and when it comes to E, that is D, B. Okay, and when it comes to F, which are A and C. Okay. So now just by listing the vertices and the corresponding adjacent vertices. So this is how we can represent a graph. Okay. So now I'll do one thing. From graph we constructed this table. Now I'll give you a table. You try to construct the graph. F, A, B, C. Okay, for F, A is there, B is there. Yeah, there are 3. Okay. For F, A, B, and C. Not that A and C. Thank you. Now this time, let me take vertex here and adjacent vertex. So here I am taking A, B, C, D, E. Total 5 vertices I am taking. Now I am writing adjacent vertices here. For this it is E, B, and for this C, this is C. Okay. And here B. D is not connected with anyone, and for E it is A. Alright, that's it. Let me take it. Is it possible to have a graph of this type? We are discussing about undirected graphs only, not the directed graphs. Not possible. What is the reason? Yeah. So here A is connected to E and B, therefore B is adjacent to A also. Okay, so here I need to take A. Now is it possible? Is it possible now? Alright. So now let us try to draw a graph. So A, so this A is here and its adjacent vertices are E and B. Let me do one thing. Let me use a different color. B and E. Alright. So now we have to establish an edge in these two. Now B is connected to C and A. Alright. So let me take C here So C, now B and C. That's it. And when it comes to D, D is isolated. It might got corona. And when it comes to E, E is connected to A. I hope we are done. That is the graph. Alright. So this is one way of representing the graphs using vertex and its adjacent vertices. Okay. So given this table, you must be able to construct the graph. Even given graph, you must be able to construct this table. Alright. And one more important way of representing graph using matrix. Right. Here we are going to discuss two types. One using adjacent in terms of vertices and another using incident vertices. Okay. So let's say you have a graph which is v comma e and the number of vertices are n. Alright. Now our adjacent matrix of the graph, what is the notation we should take? Shall we take A? So we denote adjacent matrix with A. Alright. So that is an n by n matrix whose entries are Aij, where Aij is defined like this. Of course, we are talking about undirected graph now. Even for directed graph also we will discuss. So we will take the entry 1 if Vi and Vj, if this edge is there, is an edge in G. From the ith vertex to jth vertex, if there is an edge, we denote 1 at ijth place of the matrix. Okay, otherwise we will keep 0. Okay, now let me take this graph, this one. Alright, so let me take this graph, and for this graph, let's see what is adjacency matrix. Alright, total how many vertices are here? The number of vertices are 6. So we are going to get a 6 by 6 matrix. Okay, now let us write what is A. So we need to write a 6 by 6 matrix. Now is there a connection from A to A? It means is there a loop? There is no loop, right? A is not connected to A. So we say that it is 0. A to A there is no edge. It means there is no loop. If there is a loop, then we will keep 1 here. Okay, next. Let us come to the 1 2 position. 1 2 it means, okay, here it is very important to order the vertices. Okay, A, B, C, D, E, F. I'm taking A as a first vertex, B as second, C as third, D as 4, 5 and 6. Whereas if you take these vertices in different order, you may get a different matrix by permuting the columns. Okay. So here, is A connected to B? Like, is A incident with B? No. There is no edge between A and B. Therefore, the second 1 2 entry is 0. Next, how about 1 3? That is also 0. Whereas A is connected with D, therefore 1 4 entry is 1. And A is connected with E. Oh no, it's not connected with E. Whereas it is connected with F. So we are done with the first column, first row. Now how about the second row? Okay, now let us fill the second row. Now to fill the second row, you concentrate on B. B is connected to what and what? B is connected to F and E. That's it. So F, it means it is the last position. Here you'll have 1, and E just before it you'll have 1. Now rest of them are 0 because there are no connections. And similarly, the third column, you take C and you see who are the neighbors of C. There is only one neighbor to C, that is F. Okay, so the rest of them will be zeros. Yeah. And next, you see the neighbors of D. There are two neighbors to D. One is A and other one is E. All right. Now rest of them we fill with 0. Now without looking at F, I can fill the last column. Sorry, last row. Is it last row? Last but one. Because here, I think few more information we need. But anyway, if I is connected to J, then definitely J is also connected to I. Okay, this is not a directed graph. Okay, we are taking an undirected graph here. Okay, so since the fifth entry here is 0, here the entry must be 0. Okay, and here it must be 1. And similarly, I can say that this is 1 1 and this is 0 1, and yeah, next this 1 0. Only thing I need to look at these 4 entries. What is it? Is E connected to E? No, therefore 0. And is E connected to F? No. Yeah. So this must be 0 and 0. That's it. Yeah. So if you look at adjacency matrix of an undirected graph, that will be a symmetric matrix. Okay, here you can see that A transpose will be same as A, because if Aij is going to be same as Aji in an undirected graph, if ith vertex is connected to jth vertex, it means that J is also connected to I. That is why for an undirected graph, the adjacency matrix is always symmetric. Okay, now I'll give you a matrix. You think of its graph. So this is an adjacency matrix of an undirected graph. So now draw the graph. That is the question. Now how many vertices are there? You just count how many columns are there. Yeah, there is loop at B. Okay, you draw it. Fine. So there are 4 vertices. All right. So let me name it as A, or it's better, let me take 1 2 3 4. 1 2 3 4. Okay. So now there is a loop at 1. Okay. And one is not connected to 2 anyway. One is connected to 4 only. Fine. So one is connected to 4. And next, how about the second row? It means the 2 is connected to 2. There is a loop at 2. And all right. And 2 3. 2 is connected to 3. So 3 is connected to 4. That I have to see. Yeah. 3 is connected to 4. That's it. Okay. But if you have a multi-graph, okay, if you have a multi-graph, then the entries of the adjacent matrix no longer 0 and 1. Because if you have a multi-graph, then what happens? You may have more than one edge between 2 vertices. For example, here between 1 and 4, let's assume that there is one more vertex like this. Okay, so in that case, what we have to do is At 1 4 position, what do you write? Yeah, we write 2. So at 1 4 position, we are going to write 2. Suppose if there are 3 edges, then we will write 3. Still, again, you will get a symmetric matrix only because it is an undirected graph. You understand? So between any two edges, how many number of between any two vertices, how many number of edges you have, that number we will keep it in the matrix. If you have a simple graph with loops or without loops, okay, if you have with loops, the diagonal entries may be filled with entries 1, otherwise the diagonal entries are 0. If you take a simple undirected graph. If you take a simple undirected graph with loops, then the diagonal entries are 1. The other entries either 0 or 1. But if it is not a simple graph, then you will have the entries other than 0 and 1. Only thing you'll have positive integers only. Okay, so this is what about adjacency matrix of a undirected graph. Now let us look at adjacency matrix of a directed graph. Now let me do one thing. So it is asking me to close the program. Okay. All right. Now let us talk about a directed graph. Now let me take the same graph and let me assign directions to it. Right. So this is the graph I'm taking. Now let me assign directions. This. I hope I have assigned directions to every edge. Right. Now this is a digraph. Now let us look at adjacency matrix of a digraph. Okay, the definition is same. If you have Vi, Vj edge in the graph, then ijth place will be filled with 1. But in the earlier case, we know that Vi, Vj, this set is same as Vj and Vi. So that you are getting a symmetric matrix. But here, these two are not equal. Means if you have a directed edge from ith vertex to jth vertex, it is not guaranteed that there is a directed edge from jth vertex to ith vertex. Okay, so we do not get a symmetric matrix in case of a directed graph. So now let us write the adjacency matrix for this. Right. So now so what are the edges? Let me write the edges here. How many edges are there total? 1, 2, 3, 1, 2, 3, 4, 5, 6. 6 edges are only there, right? So let me denote those 6 edges. So one is AD and another one is FA. AD is 1, that's it. Next, let me think about B. Starting at B, BF, and starting at C, there is no edge starting at C, alright. Then starting at D, no edge. Starting at E, yeah, EB is there. And ED is also there. And how about F, F, A, and FC is also there. But now FC is closed, right? Because you are not here. Alright. So now AD. Where is AD? There is no A, right? So these are all 0. AD, yeah, here I'll have 1. Because the first vertex is connected to fourth vertex, 0 and 0. We got 6. Next, 0, B is connected to F. So 1. Oh, is it? No. 0, 0, 0, 0, 1. And next, there is no edge starting at C, therefore all these guys will become 0. And how about D? Yeah, I think there is no edge starting at D also. So fourth row is also 0. So how about the other one? I mean, starting at E, EB and ED. Okay, 0, 1, 0, 1, 0, 0. Right? Just one more. Starting with F, FA. Okay, this is 1 and FC. So now this is what the adjacency matrix for this directed graph. Okay, so adjacency matrix of a directed graph need not be symmetric, but for an undirected graph you'll get a symmetric matrix. All right. So now I'll give you a adjacency matrix of a directed graph. Now you think about the graph. All right. Okay. Now this is an adjacency matrix of a directed graph, digraph. So what is a digraph here? There are 4 vertices, A, B, C, and D. Okay, let me name it. So first, second, third, fourth. Let me name it like this. Now let us draw the directed edges. So starting at 1, is there any edge starting at 1? It is also mixed graph at CD. What do you mean by mixed graph? I am saying it is a directed graph. No? All edges are assigned directions. Anyway, so let me see. Let me take an edge starting at 1. So that is 1, 2. Right? From 1 to 2 there is an edge. That's it. Now the edge starting at 2, that is 2, 3. Okay, that's it. We are done. Next, let me come to 3. The edge which are starting at 3 or 3, 1. And there is one more, 3, 4. And next, the edge which is starting at 4. Okay, from 4 for every other vertex we have edge. 1 to 4, then 1 to 2, sorry 4 to 2, and similarly 4 to 3. That's it. There is 4 to 4. Okay, there is a loop. Okay, are you saying that since there is a loop, it is an mixed graph? We don't really worry about loop. Whether you give direction or don't give direction, doesn't matter. Okay. This is not, see, we say it is a mixed graph if you find a directed edge and an undirected edge. Okay, loop, since I said it is a digraph, the loop is also given direction. But it doesn't matter whether you take it like this or like this. Okay, because it starts at 4, ends at 4 only. The only thing it matters is whether you are rotating in an anti-clockwise direction or clockwise direction. All right. So this is the diagram for that adjacency matrix. All right. And there is one more representation of a graph using incidence matrix. So shall we discuss or shall we stop? I'll simply illustrate one example for an incident matrix with that I'll stop. Okay. Now let us discuss about incidence matrix. So now it based on the edges and vertices. Okay. So here, for example, you have a graph. Let me explain with an example first. Let's say you have a vertex 1, 2, 3. Right. Let me take one more. So 1, 2, 3, and this one, let me take it as a 4. Okay. So how many edges are here? Total there are 3 edges, E1, E2, E3. And how many vertices are here? There are 4 vertices. You can see the number. Alright. So now we are going to write an incident matrix like this. We denote with M. So first we write H1, H2, H3. There are 3 edges. And how many vertices are there? 4 vertex. Therefore V1, V2, V3, V4. But we don't explicitly write every time, okay? We simply write the matrix. So you have a matrix of size 4 by 3. Now, if the edge 1 is incident with V1, we will keep 1 here. Is edge 1 connected to 1? Yes. Therefore, we keep 1 here. Okay. Now, is edge 2 incident with 1? Vertex 1? Yes. Therefore, we keep 1 here. How about edge 3? Edge 3 is not incident with 1. You understand? Edge 3 is incident with 2 and 4, but it is not incident with 1. Therefore, we keep 0 here. Similarly, we will come to the second vertex. Right? Now, what are the edges which are incident with the second vertex? Only E3 is incident with it. Therefore, here we will get 1. The rest we will get 0. You can see that E1 is not incident with the second vertex. E2 is not incident with the second vertex. Right? Now you come to V3. So if you look at this vertex 3, only E1 is incident with it. Therefore, here you'll have 1. The rest becomes 0. And how about V4? There are 2 edges which are incident with it. One is E2, other one is E3. Therefore, 1 here, here it is. Now this is what? Incident matrix. Okay. If the edge EI, okay, if the edge EJ is incident with VI, then IJ entry will be 1. Okay, otherwise IJ entry is 0. If the, let us say if the second edge is incident with 1, then 1, 2 element is 1. If the second is not incident with 1, then 1, 2 element is 0. Okay, so this is what we call incident matrix. Okay, now this time I will give you a matrix, incident matrix. You try to draw the graph. Can we have an edge which is incident with only one vertex? That can be maximum a loop. Yeah, so because here you see, you look at this column, edge 1 is incident with only one vertex, right? Therefore, what is it you'll have? You'll have a loop, that's it. Let me take V1, V2 and V3. So let me name it as H1, incident with 1. Okay. And the edge which is incident with 3, I call it as E3, and this is E4. Sorry, E2. Is it E2? Oh, there is a double loop. There is a double loop at V2 is isolated. That's it. There is a double loop at V1. This is edge 2, and this is V2. Okay. See, I mean, we can easily know whether that is an edge or a loop. You look at that column. Okay, if it is an edge, definitely it should connect to two vertices. Okay, for example, you see E1, it is connected to 1 and 3. Okay, E2 is connected to 1 and 4, and E3 is connected to 2 and 4. If you have only 1 in the column, it means what? That is a loop. You see, there is only 1 in the first column. Even in the second column, the same thing. Even in the third column, the same thing. Okay. Now I hope we can think about this. What if I give it like this? Can I have 3 ones here? How about this? So there are 3 vertices, right? V1, V2, V3. So edge 1 is incident with V1 and V3, right? Okay, so let me name it as E1. This is edge 1. Next, edge 2 is incident with V2 and V3. Now, how about this one? If you have all ones here, it has to be incident with 1, 2 and 3. Is it possible? It's not possible, right? Okay, so let me change it. So let me make this as 0. It can't, an edge can't be incident with the 3 guys, no? So if I have 1, 1, 0, then I'll get K3, H3. Alright. So this is what an incidence matrix is. Okay. So these are the representations of graph. We represent with adjacency list and adjacency matrix and incidence matrix, 3 types. I think when it comes to adjacency list, I only discussed for undirected graph. I didn't discuss directed graph, no. So in the case of directed graph, we take initial vertex at one place and terminal vertices at other place. Like in undirected graph, what we are doing, we take a vertex and the corresponding adjacency guys, adjacency vertex, right? But when it comes to a directed graph, you can take initial vertex at one side and the the corresponding terminal vertices you can write. That is how you can write adjacency list in a directed graph. Okay, so I'll stop it here.